Okay, thank you for the introduction. I'd like to acknowledge my co-authors, my PhD students, Sassan Zalapour, and PhD student Hassan Safarian, who couldn't be here, but I'm presenting in their place. So I'd like to talk to you first a little bit about the motivation for this work. Then I'll look into our lookup table method for doing nonlinear compensation, give you a brief look at our experimental setup, and then finish with our look at experimental results for what we call the full-sized lookup table and a reduced side. So first I'd like to talk about the motivation, and that is, why are we looking at all-silicon solutions? We saw in the plenary from Acacia that using an all-silicon solution gives us a smaller footprint, potentially lower cost, lower power. And all of this is coming because we can do integration on these all-silicon devices. But there are challenges in using all-silicon as we move to higher order modulation formats. So the results I'll be presenting today refer to a traveling wave modulator using a single drive push-pull. There is a slow wave electrode in the design. So the challenges in pushing the bandwidth and the QAM order have to do with looking at the operating point and the DSP mix that we use in order to compensate for the impairments. And why this is particularly difficult in silicon photonics versus other Mach-Zehnder modulators is because the bandwidth and the V-pi of the modulator are intrinsically related. So if we try to increase one, we'll have a different impact on the other. And that's because the V-pi in a silicon modulator depends on the bias point, the operating point of our modulator. So there are many different nonlinear effects. Some of them are for any Mach-Zehnder modulator. If we look in the time domain, we have the sinusoidal characteristic. Of course, we also have RF amplifiers that could be operated in saturation, and these will have effects on the constellation, especially higher order model constellations, which have asymmetry in the constellations. If we look in the frequency domain for the silicon modulator, I can give you one example of where some other kinds of nonlinearities may be introduced. For instance, here we have simply the frequency response, small signal, for different bias voltages. And we can see that if I change the bias voltage, I'm actually changing the frequency response. This is small signal. Now, if I'm swinging my data signal across something from 0 to 2 volts, that means that the system is inherently nonlinear. It can't be described by a single frequency response. And there are, of course, other nonlinearities in the silicon photonics phase modulator, which could also contribute to a requirement for nonlinear compensation. So the solution that we're looking at in this paper is a joint. Of course, we're using all the linear methods that we can to compensate our performance, but we're also looking at nonlinear predistortion. And we're looking in particular at a lookup table to be a methodology for combating the nonlinear. And of course, a lookup table is a very simple idea. If I have a system where I put in a square QAM constellation and the output is deformed, what I can do is I can change my input so that it's no longer square, hoping that at the output, when it's with the receiver, it'll be square, easier to treat. And so we have this lookup table, which is my way of determining, according to what constellation is put in, which constellation point is put in, where I should deform it. However, because of the time-varying nature of the nonlinearity, what we'll do is we'll have a lookup table that doesn't take a single constellation, but it looks at a sliding window of a certain memory length of that constellation. So for instance, in this illustration, we're looking at a memory length of 2, or memory depth of 2 in the lookup table. And as I slide along, I'll see which 3 symbols are in this sequence. And in the table, that will become the address for my table. And in the table, I will have a correction factor for the middle symbol. So this is my mapping. So my mapping is not for a given constellation point giving another constellation point, but one that appears in a sequence giving a different correction. It's important because it impacts greatly on the scalability of the solution. So there are 2 things that make lookup tables difficult. First of all, it's size, but what influences size is the size of the constellation, so the number of points in the constellation, and also the memory depth that I choose to implement in my lookup table. So they both impact on performance. And if we consider a square constellation where the symbols have complex values, this also leads to large size. And in the table here, I just look for different memory depths for 16 QAM, for instance, what the size of those lookup tables would need to be. So one way to reduce the complexity of the lookup table is to use, instead of a complex two-dimensional LUT where I look at the I and Q coefficients, that I treat the I separately from the Q in two different lookup tables. So it doesn't matter how they come together on a single point, but where they are, either in the row or the column, I will correct that. And that leads to something like a square root reduction in the size of the lookup table. Of course, it's suboptimal, but even for large LUT size like 256 QAM, this can still be complex. So one of the things I'll be looking at today is also how we can prune them, and this is not unlike what we heard in the first talk, where they looked at different kinds of strategies for pruning away some coefficients. So we do the same thing in our lookup table. So that'll be called the full-size LUT, which is full size, but it's still this reduction to the one-dimensional instead of a full two-dimensional lookup table, and a reduced one where we're trying to prune them in different ways. So the idea is, at least from the 1D, that we can approach 256 QAM, which are the results I'll be presenting today. So this is our experimental setup. I don't have time to go into the details, but it's available in the paper. But this is, we have it, we run through a characterization phase where we populate the lookup table. And then once we've populated the lookup table, we run the system again and see how the lookup table has improved performance. So I'm going to present results always for two scenarios. One is the 20 gigabits per second, 256 QAM. The other is 20 gigabaud, 256 QAM, and 40 gigabaud. So first we start with linear compensation only. These are the distorted distortions we find. Here in green, I showed the observed error. And the observed error is more asymmetric with the 20 gigabaud than the 40 gigabaud. And the reason is because at 20 gigabaud, I can drive my driver with a stronger peak-to-peak voltage, and because of that, I'm looking into saturation of our RF amplifier more in all likelihood. I'm running out of time. I'm going to have to go through this quickly. I'll look at different lengths of memory depth. So in the green there on the side, I have one example of the distribution of error. And now I just present across all of the possible points, different pattern numbers, what the error is. And as I go from left to right, I'm going from memory depth of 3 to 5 to 7. There are many things that are going to influence how the error distribution happens. One is how system memory, the actual memory of the system that is under test, varies compared to the memory depth of the lookup table. So one would expect that it would get better as I go from 3 to 7, because by 7, maybe I've definitely covered the memory depth. And maybe I'll stop improving when I get to a certain length. But the other part that influences is noise averaging. When I have a smaller lookup table, when I'm actually populating the lookup table, I have many examples. And I have many examples of the same sequence appearing, and therefore I can average out the noise, and I'll probably get a more accurate correction. Whereas on the larger ones, these sequences are occurring less often. So that's one reason for this behavior. So here again, if I only use linear filtering, this is what I am observing at the receiver. So in this case, I give an example from size 7, a memory depth of 7 for the lookup table, and this is the predistortion pattern that I'm putting in to my system, and then this is the output constellation after this correction. So here we've gone through and looked at the bit error rate curves for the 20 gigabaud 256 QAM. We have in green the linear only, and then as we try different size lookup tables, the longer it's getting, we are getting some improvement in power, but in performance, but from 5 to 7, it's not necessarily that important. And here's for the 40 gigabaud. Again, we see a similar trend, and with this case 128 QAM, we can again get below the 20% threshold, even with a LUT of length 3. So when I said we want to look at how we might do reduce the complexity further, what we'll do is thresholding to only keep LUT entries which are correction factors which are large enough to have an important impact, not unlike the last one mentioned in the first speaker today about how he was pruning the Volterra series. So in this case, we're using something similar for the lookup table. So I set a threshold that says I want to eliminate 20% of the entries in my table. What threshold should I use? And I can go through that and vary it, and that's what we sweep through, pruning more and more of the entries. So here's the results for 20 gigabaud, 256 QAM, and we can see that we can reduce the lookup table even from size 3 down to 60% of the original size without having any impact on performance because some of these are either so noisy that they're not really helping us or are just simply less critical. In terms of the 40 gigabaud, now we're looking at a LUT size memory depth of 5 that was examined to make sure that we had some margin in keeping below the effect threshold. And even in this case, we could go down to 70% coverage and still get good, robust performance. So you'll recall that one of the last comments from the first speaker was to be careful about what you're using as your training set. And in this case, we started with a certain PRBS, and we wanted to vary the PRBS order to see if our results would be consistent across that. And so we can see that the improvement that we obtained was valid so that our training set was not biasing our results. So in conclusion, we've looked at a silicon photonics IQ modulator that was able to perform below the 20% effect threshold at 256 QAM, 20 gigabaud, and also at 40 gigabaud when the bandwidth constraints also kick in. And we saw that in reducing the size, we used a one-dimensional LUT, which was sufficient for this work, and also we were possible to reduce the size further. And I thank you for your attention.